What if you could turn an STM32 microcontroller into a mouse or a keyboard, without any additional hardware or drivers? Just plug it into your computer via USB, and the computer recognizes it as an input device instantly. That is exactly what we are going to do in this video. Hello and welcome to Controllers Tech. This is the third video in the STM32 USB series. In the previous video, we covered how to use the USB device in HID mode. We connected a joystick via the ADC, and the computer was able to recognize the STM32 as a game controller. Today, we will continue using the USB device in HID mode, and we will see how the STM32 can act as a mouse and a keyboard. These two will be covered separately. This video is divided into two parts. In the first part, we will see how to use the STM32 as a mouse using a joystick. In the second part, we will see how to use the STM32 as a keyboard using a 4x4 keypad. We will continue from where we left off in the previous video, so make sure you watch that first. The hardware connections and the CubeMX configuration that were done for the gamepad will remain mostly the same for the mouse project as well. Here is the wiring diagram for the mouse part. The joystick will be used to control the mouse pointer, just like it was used for the gamepad in the previous video. The X-axis output is connected to pin PA0, which is ADC1 channel 0. The Y-axis output is connected to PA1, which is ADC1 channel 1. The button output is connected to PA2, which we will configure as a digital input. In addition to the joystick, two more buttons are added to act as the left and right mouse buttons. These are connected to pins PA6 and PC4 respectively. Both buttons are connected to a common ground on the STM32 board. By default, these pins are pulled high. When a button is pressed, the respective pin is pulled low. In total, there are three buttons: left click, right click, and middle click. The middle click is the button already present on the joystick. As mentioned, we are continuing with the gamepad project from the previous video. I have already loaded that project in STM32 Cube IDE. The first thing we will do is rename this project. I am going to call it STM32 USB Device HID Mouse. When renaming, make sure the Update References box is checked, so that the name is updated in all the relevant locations inside the project. Now that the renaming is done, we will also rename the IOC file. It has been renamed as well. Now let us open the renamed project in STM32 CubeMX, and start with the configuration. The connections are the same as we covered in the previous video. There is one ADC with two channels, where the data from the X and Y axis of the joystick will be read. There is also an input button connected to pin PA2, which is the button present on the joystick, and this will act as the middle button of the mouse. Other than that, we need to configure two more pins as inputs for the left and right click buttons. I will also rename the pins according to their functions. Pin PA6 will be the left button, pin PC4 will be the right button, and pin PA2 will be the middle button. Now go to the GPIO configuration and enable the pull-up resistor for the two new button pins we just configured, which are PA6 and PC4. That is all we need to configure in STM32 CubeMX. Let us now generate the updated project. The project has been generated, so let us go back to STM32 Cube IDE. Now open the USB device HIDC file and scroll down to the mouse report descriptor section. After regenerating the project, you can see that the mouse descriptors have already been generated. Since we are using the STM32 as a mouse, we do not need to modify these descriptors at all. I have already explained these descriptors in detail in the previous video, but I will quickly go over them once more. Here, the usage has been set to mouse. Since a mouse is a pointing device, a sub-usage page for the pointer is created inside the collection. The collection starts with the button configuration. The usage page is set to button. There are 3 buttons in total, so the usage maximum is set to 3. These 3 buttons are the left click, the right click, and the middle click. Each button can either be a 0 or a 1, which means there are 2 possible logical values. The report size is set to 1 bit since each button only needs a single bit to represent its state, and the report count is set to 3 because there are 3 buttons in total. This means 3 bits in the report will be occupied by the button data. Since a byte has 8 bits and only 3 are used by the buttons, the remaining 5 bits are filled with padding using constant values. Next comes the data for the x-axis, the y-axis, and the scroll wheel. The value can range from -127 to +127, so the logical minimum and maximum are set accordingly. The report size is set to 8 bits since each value occupies 1 byte, and the report count is set to 3 because there are 3 values, 1 for the x-axis, 1 for the y-axis, and 1 for the scroll wheel. This data is relative, meaning each value represents a change in position rather than an absolute position on the screen. Therefore we cannot directly pass the ADC value to the HID buffer. The ADC gives us an absolute value, but the mouse descriptor expects a relative change. So we will write the code in a way that only the relative change in position is passed to the buffer. After this, there is a motion wake-up section in the descriptor. We will not cover that in this video, but it is a standard part of the mouse descriptor, so we are leaving it as it is. So in total, we have 4 data bytes in the report. The first byte is for the buttons, the second byte is for the x-axis, the third byte is for the y-axis, and the fourth byte is for the scroll wheel. Even though we do not have a physical scroll wheel, we still need to send a value for it. We will simply send 0, and since the data is relative, a value of 0 means there is no change in position. If you check the HID endpoint size in the header file, you will see it is defined as 4, which matches the 4 bytes we just described. Now let us go back to the main file. Here we will create a new HID buffer with 4 elements, and initialize all of them to 0. We will also create an array to store the ADC values received from the ADC peripheral. In the previous video, we configured the ADC to receive 8-bit data, so the ADC values will range from 0 to 255. Now, since the x and y-axis data must be relative, we cannot send the raw ADC value directly. Instead, we will send how many pixels the mouse pointer should move when the joystick is tilted past a certain threshold. So if the joystick is tilted in one direction on the x-axis, the pointer will move by 5 pixels in that direction. If the joystick is tilted in the opposite direction, the pointer will move by -5 pixels. In any other case, the value will be 0, meaning there is no change in the pointer position. We will apply the same logic for the y-axis as well. Now, regarding where each value is stored in the HID buffer, the 0th element will store the button data, the first element will store the x-axis data, the second element will store the y-axis data, and the third element is for the scroll wheel. Since we do not have a physical scroll wheel, the third element will remain 0. Since we are storing negative values in the HID buffer, we need to change its data type to signed 8-bit integer. Now let us go to the main function. Before sending the data via HID, we need to handle the button inputs and store the result in the 0th element of the HID buffer. The left button occupies the first bit of this byte, the right button occupies the second bit, and the middle button occupies the third bit. Depending on which button is pressed, the corresponding bit must be set in the 0th element. At this point, our report is ready. Now we will send this report using the USB HID send report function, passing the buffer and a size of 4. After sending the report, make sure to reset the 0th element back to 0, so that the button state does not remain set in the next report. You may notice a build error in the send report function. That is because it expects a pointer to an unsigned integer, so we need to typecast the buffer pointer accordingly. After doing that, the project should build without any errors. Now let us flash the project to the STM32 board. Once flashed, you can see the STM32 development board with the joystick in the bottom left corner of the screen. Notice how the cursor on the computer responds to the joystick movements. The cursor movement is smooth and responsive. Now let us test the buttons. The left button is responding correctly. And the right button is also working as expected. So we have successfully implemented the STM32 as a USB mouse. The joystick controls the cursor movement using relative ADC data, and the three buttons handle the left click, right click, and middle click. The project is working correctly. Now we will move on to the second part of this video, where we will emulate the STM32 as a USB keyboard. We will continue with the mouse project and make changes to it directly for the keyboard implementation. First, let me copy the mouse project somewhere else as a backup. Now I am renaming the project to USB HID keyboard. Make sure to rename the IOC file as well. Also delete the debug configuration and the debug folder from the previous project before we proceed. Now, before we go into the configuration, let us understand how the keypad works and how it is connected to the STM32. I am going to use a 4x4 membrane keypad for this project. This keypad has a total of 8 pins, 4 for the rows and 4 for the columns. Whenever a button is pressed, the respective row pin and column pin are connected together internally. To detect which button is pressed, we will use a simple scanning method. We will set all 4 row pins as output and all 4 column pins as input. All the row pins will be set high by default. Then, we will pull one row low at a time. If a button in that row is pressed, the column pin connected to that button will also go low, because the row and column pins are now connected through the pressed button. By reading all 4 column pins, we can determine which button was pressed. For example, if we pull row 1 low and button 1 is pressed, then column 1 will also read low. This tells us that button 1 was pressed. Similarly, if row 3 is pulled low and the number 8 key is pressed, then column 2 will read low. Since row 3 is low and column 2 is low, we know that the key pressed is number 8. Now let us look at the connections on the STM32. All 8 pins of the keypad are connected in a single line to make the wiring easier. The 4 row pins are connected to PB1, PC5, PA7, and PA5, and these will be configured as output. The 4 column pins are connected to PA3, PA1, PC3, and PC1, and these will be configured as input. Now let us open the project in the STM32 Cube MX. First, disable all the GPIO and ADC pins that were configured for the mouse project. Then configure the row pins. Set PB1, PC5, PA7, and PA5 as output and rename them as R1 to R4. Next, set PA3, PA1, PC3, and PC1 as input and rename them as C1 to C4. Now go to the GPIO configuration. Select all the row pins while holding the Control key, and set the initial GPIO output level to high, since we want all row pins to be high by default. For the column pins, enable the pull-up resistor so that by default they read high. When a column pin connects to a row pin that has been pulled low, it will read low. Otherwise it will remain high. That is all the configuration we need. Let us now generate the project. The project has been generated, so let us go back to STM32 Cube IDE and open the USB device HIDC file. You will notice that the mouse descriptor has been generated again, because STM32 CubeMX generates the mouse descriptor by default. We will need to modify this descriptor for the keyboard. Now let us understand how the HID data is sent for a keyboard. The keyboard sends a total of 8 bytes of data in each report. The first byte is for the modifier keys, the second byte is reserved, and the remaining 6 bytes are for the actual key codes. These 6 key code bytes allow us to send up to 6 simultaneous key presses at a time. For today's demo we will only use 1 key code at a time, but the descriptor supports up to 6. Now let us understand the modifier keys. I have the HID usage tables document open here, and I will leave the link to this document in the description. If you scroll down to the keyboard section, you can see the list of all available key codes and modifier keys. At the bottom of this list, you will find 8 modifier keys ranging from E0 to E7. These include the control keys, shift keys, alt keys, and the GUI keys. Each of these modifier keys occupies 1 bit in the modifier byte, so all 8 modifier keys fit into a single byte. Now let us modify the mouse descriptor to work as a keyboard descriptor. The first change is the usage value. Since we are now using a keyboard, the usage must be set to 06, which represents a keyboard. This was also explained in the previous video, where 02 represents a mouse and 06 represents a keyboard. Since a keyboard is not a pointing device, we will also remove the pointer-related part from the descriptor. Next, the usage page must be set to the keyboard. According to the HID usage tables document, the keyboard usage page is 07, which is shared between keyboard and keypad. Now we will configure the modifier byte. The usage minimum is set to E0, and the usage maximum is set to E7, which is the range for all 8 modifier keys as defined in the document. The logical minimum and maximum will be 0 and 1 respectively, since each modifier key represents a single bit that is either pressed or not pressed. The report size is set to 1 bit since each modifier key occupies 1 bit, and the report count is set to 8 since there are 8 modifier keys in total. The input data type will be absolute. This completes the modifier byte. Next comes the reserved byte. We will fill this entire byte with constant values, as it is not used for any actual data. Finally, we have the 6 key code bytes. We also need to add the usage minimum and maximum for the key codes. The usage minimum is set to 0 and the usage maximum is set to 65 hex. According to the document, key codes start from 0 and go up to 65 hex, which covers all keys on a standard 104 key keyboard. The logical minimum and maximum are also set to 0 and 65 hex respectively, since the key code can be any value in that range. The report size is set to 8 bits since each key code occupies 1 full byte, and the report count is set to 6 since there are 6 key code bytes in total. Unlike the mouse data, this is not relative data. It will be sent as an array of values, so we need to set the input type to data array. This completes the keyboard data collection. We will close the collection and remove everything after it. In total, our report descriptor now has 43 entries. Open the USB device HID header file and update the report descriptor size to 43. Also update the HID endpoint size to 8, since the HID buffer will now send 8 bytes in total. That is all the changes needed in the USB HID files. Now let us go back to the main file. We will delete the code from the mouse project and define a new HID buffer with 8 elements as an unsigned integer array. To read the keypad data, we will create a new function called scan keypad. Inside this function, we will reset one row at a time while keeping all other rows high, and then read all 4 column pins. Based on which column reads low, we will determine which key was pressed. We will start by resetting row 1 while setting all other rows high. This ensures that only one row is active at a time. After setting the rows, we will wait for 1 millisecond to allow the pins to settle, and then start reading the column pins one by one. Now, we cannot simply store a number like 1 directly into the HID buffer. We need to find the correct key code for each key from the HID usage tables document. For example, the key code for the number 1 on a keyboard is 1E, and for number 2 it is 1F, and so on. Instead of storing the key code directly into the HID buffer, we will create two variables, one for the modifier byte and one for the key code. We will store the detected key data into these variables first. So if column 1 is low while row 1 is reset, it means the number 1 key has been pressed, and we store 1E into the key code variable. If column 2 is low, the number 2 key was pressed, so we store 1F. If column 3 is low, the number 3 key was pressed, so we store 20. If column 4 is low, the letter A was pressed, and its key code is 04 as defined in the document. We will follow the same logic for the remaining rows. For row 2, column 1 represents the number 4, column 2 represents the number 5, column 3 represents the number 6, and column 4 represents the letter B. The same structure is followed for row 3 as well. For row 4, we will do something a little different. Instead of mapping the star key to its actual key code, we will treat it as the left shift modifier key. The left shift key is a modifier key, and according to the HID usage tables document, it occupies bit 1 of the modifier byte. To set this, we perform a left shift of 1 position on the value 1, or we can simply write 02, which indicates that bit 1 is set. Either way, when the star key is pressed, the modifier variable will be set to represent the left shift key. Column 2 of row 4 represents the number 0, whose key code is 27. Column 3 represents the hash key, but instead of mapping it to hash, we will use it as the backspace key. The key code for backspace is 2A. Column 4 represents the letter D. That completes the scan keypad function. Now let us go to the main loop. Here we will first call scan keypad so that the key code and modifier variables are updated based on the current key press. Then we will store the modifier variable into the 0th element of the HID buffer and the key code variable into the second element. Finally, we will send the HID buffer using the send report function, and this time we are sending 8 bytes in total. The project builds without any errors, so let us flash it to the board. I have a text editor open to test the keypad, and you can see the hardware in the bottom left corner of the screen. I will press the keys in order, 1, 2, 3, A, 4, 5, 6, B, 7, 8, 9, C, then the star key which acts as the left shift key. Next is 0, followed by the hash key, which deletes the last character, and finally D in the end. All the keys are being registered correctly in the text editor. Now let us test the shift key. While holding the star key, which is mapped to the left shift key, I will press A, B, C, and D. You can see that the letters are being typed in uppercase. The shift key is working correctly, and so is the backspace key. The STM32 is successfully behaving as a USB keyboard. We will make one small modification here. Instead of mapping the 0 key on the keypad to the number 0, we will use it for the space button. The key code for space is 2C, so we will update that in the scan keypad function. Let us build and flash the project again. Now notice what happens when the 0 key is pressed. You can see a space being registered in the text editor, which confirms that the change is working correctly. The keypad is working well for demonstration purposes. However, there is a lot more that can be done with keyboard implementation, as there are many more key types available. I am planning to do a dedicated video for the keyboard in the future, where I will connect an actual keyboard with more than 100 keys to the STM32 and try to make all the keys work using the HID class. So we were able to successfully emulate the STM32 as both a USB mouse and a USB keyboard using the USB device HID class. The joystick, connected via ADC, was used to control the mouse pointer, and the 4x4 membrane keypad was used to send key presses to the computer. The keypad used here was only for demonstration purposes, and a more complete keyboard implementation will be covered in a future video. In the next video, we will implement the STM32 as a USB mass storage class device, where the STM32 will act as a flash drive when connected to a computer. That is all for this video. You can download the project files from the article linked in the description. Leave a comment if you have any questions. Keep watching, and have a nice day ahead.